Okay, so last time we looked at this situation, right, where we had $2 in year 1 through 4 and then 102 in year 5. So we're going to go to the next Bob question, which is suppose the same friend offers you $2 every year for forever. What would that be worth today? So just to be clear, right, we're talking about infinite money. This is $2 every year for eternity. You add those up, you get infinity. So this is infinite dollars. And actually, if you think closely about situation 7, right, there was no, right, this situation where we have 2, 2, 2, 2, 102, that reduced to 100. And if we look at the logic of this, right, the 102 reduces to 100, which turns to 102, which reduces to 100. And there was nothing about this logic that changed as we added years. Right? No matter how many 2's we add, we're always going to be worth 100 at the start of the year. And so naturally, if I have $2 every year for forever, this is going to be worth $100. So you'll think, wow, how can infinite dollars be worth finite $100 now? And it's actually not as crazy as you think. Basically, if I put $100 in a savings account and leave it there forever, it will turn to infinity, right? If we let time pass forever, then money will grow to be infinitely large because interest works like that. And so this is really the same problem, but in reverse, right? Instead of saying, well, if I put money in a savings account and leave it there forever, I have infinite money. What this is saying is, if I have infinite money, how much would I have to put in a savings account to get there? And the answer is quite simply $100 in this case, right? Because if I put $100 in a savings account, it will grow to 102. I remove $2 and I have 100 left over, which can then grow to 102 next year. So receiving $2 every year requires a $100 deposit at 2% interest rates. And so even though this pays for forever, we can come up with a nice round finite number to demand today to make this work. And that's going to be really important in a minute because we're going to use combinations of pays forevers to get payments for a particular length of time. Okay, so let's go to situation 9 now. Suppose the same friend offers you $2 every year for forever starting in year 2. What would that be worth today? So to be clear, we have $2 every year forever, but it doesn't start right away. It gets delayed by a year, right? Usually $2 would show up in year 1. In situation 8, $2 showed up in year 1, but now it's showing up in year 2. So to understand this situation, we have to think about what it looks like in year 1. So if we let a year go by, after a year, this looks exactly like situation 8. Right? And we know what situation 8 is worth. Situation 8 is worth $100. So this situation we know is worth $100 in year 1. So something worth $100 in year 1 is going to be worth something less than $100 in year 0. And exactly how much less we can figure out using the CD that's available, right? So this CD turns $1 to $1.02, and we have $100. So if I take $100 and I divide by 1.02, that tells me how many CDs I need to buy, and then I'm going to multiply it by the price per CD and get $98, right? So, and we kind of knew it would be about that, right? Since 100 turns to 102, so 98 and a little bit more will turn to 100. But this is a really important concept to understand because what we've done here, right, is this is 2, 2, 2, 2, 2, 2, 2 forever, right? Forever. So we turn 2222222 forever into $100 in year 1, which then turns to $98 in year 0. So we've collapsed this to this in one step, and then we've turned this to this in another step. Right, so we're moving money through time here, and we're moving many payments to one payment here. And this is going to be kind of the hallmark of these kinds of questions, is that we will be combining steps together to do increasingly complicated things. So there's some implications of this, right? So money today is not worth the same as money in the future, and we've talked about that over quite a bit. How much less depends on the opportunity cost of funds. So how much money could you receive if you invested at prevailing market rates? And it's also important that the same cash flows cost the same amount. And so those are all key features in finding value using the time value of money. And often we'll use we'll replicate the cash flows of a security using a different security. So for example, if we have maybe a bond, we can replicate a corporate bond as a series of withdrawals from a checking account. And so if we know how much money we'd have to deposit in a checking account to get the same cash flows as a bond, then we know what the price of that bond should be. So that's a replication argument. It's based on no arbitrage. Arbitrage is a word that means essentially either paying nothing to get something in the future for free, or getting paid to do nothing in the future, right? So if I get $1 for not doing anything anytime in the future, that's free money, and I will just do that over and over and over again and become infinitely wealthy. Or alternatively, you can think about it as buying something for $, and the thing obligates you to nothing. Right, so certainly it's very easy for me to buy a security that says I promise to mow your lawn, and I might buy it for -$5, but then it obligates me to mow the lawn. So think about it as I promise to mow your lawn, except actually I don't have to, but give me $5 anyway, and someone's selling. So all of this thinking in the Bob situation actually leads to some mathematical formulas, right? So, and they're pretty simple, right? We know if I have cash now, right? If let's say I have $100, the interest on that $100 is going to be R times 100, right? And so the final result is going to be 100 plus R times 100. Which if we factor out a 100 is 100 times 1 plus R. Oops. Okay, and we've established as well that if we do it again, it looks like this. Oh, that's not 10R, it's 1 plus R. And so that turns out to be, with a little, some simplification, 1 plus R squared. And so, in fact, it works like this for n years. And that's doing interest going forward, right? So when we invest money now and save it until the future, then it gets bigger by a factor of 1 plus R to the n. Well, you can imagine, right, what if I do the backwards thing? What if I borrow money now, what if I have some amount of money I'm trying to get to in the future, and I want to know what it would be worth now? Well, if we do algebra, right, so I would say the value in year 0, we're going to call that the present value. Oh, sorry, so this is the value in the future, right? So the future value of this money is equal to the present value of the money Okay, well, 100 was just our example. So for any dollars today, you just take the value in the present, multiply by 1 plus r to the n, and you get the value in the future. Well, obviously, right, if I divide both sides by 1 plus r to the n, this cancels, and you get this. Okay, so the present value is the future value divided by 1 plus r to the n. So to go forward, we multiply, and to go backwards, we divide. And all it is just some simple interest rate math, right? I have the principal and I have the interest, and so if I do principal plus interest, it's going to look like 1 plus r, because 1 stands for principal and r stands for interest. And if we do it twice, we have 1 plus r and then 1 plus r again, because we have, if you think about FOIL, right, I have principal plus interest plus interest plus interest on the interest, right? I get, over 2 years, I get the interest twice, and I get interest on the interest, and I get my principal back. And that works for as many years as we like. So we actually, really, you can accomplish this class with about 5 formulas, maybe 6, it depends how you define them. And we have just learned 2. So here's the future value formula, where we multiply, finding the future value of some money in the present, and then the present value formula is taking the future value and dividing by this interest rate factor. We end up doing the present value formula more because often the things we're considering are planning on paying us in the future. Right? If I purchase a stock, I'm interested in having it pay me in the future. And so I want to know what the value today is of these payments I'm expecting in the future. And so we can treat the time money is received as a units conversion problem, right? So if I have 0 degrees centigrade, we know that that's the same as 32 degrees Fahrenheit. And actually, there was in the early days of the internet, I was on it was a bulletin board system, but it used a software called Telnet. It was a text-based internet. There weren't websites. You would log into a university or a private company that had a server available, and you could text communicate and interact with some software that way. And there was a big argument between some Wisconsinites and some Canadians over whose hometown was colder, and they both claimed that negative 40 degrees happened. But the Canadians are claiming negative 40 degrees centigrade is colder than negative 40 degrees Fahrenheit, and the Wisconsinites disagreed. And we know that centigrade degrees are bigger, but Fahrenheit starts at a higher number. And so what do you get? Well, it turns out that negative 40 is the exact point in which they're equal, so everybody was talking past each other. But in that case, that's an example, right, where units are different, and we have to do a conversion from one to the other if we want to be mutually intelligible. So same thing with the time value of money. If you have a cash payment, like $100, you need to know the time it arrives, right? So every cash flow has an amount and a time, and you can't do math on cash flows arriving in different times. If I have $10 today and $10 tomorrow, that does not mean I have $20 ever, right? It's not even true. It's not even numerically accurate, because if I put my $10 in the bank and maybe earned a penny interest, now I have $20.01, and that's accurate. Or maybe it's $19.99 because I have to borrow and it cost me a penny, right? Adding money from different times is never appropriate, because it's like saying I have 10 packets of ketchup and 10 Ferraris, and that makes 20 somethings, right? It doesn't make sense. Same thing with this. So we need things to be in the same year to do math on them and to combine them. And often what we do is move things to the present, to year 0, and then add them there. So if we just take everything in present value terms, then we can combine it and get to a final number. Okay? So if I have $108 in year 2 and R is 4%, what is the value of that today? So I would, says this is a future value problem. 108 is a value in the future. So I take my 108 and divide by 1.04 because that's 1 plus R, right? And it's squared because we have 2 years. And we get $99.85. So again, why is this not $100? Well, if I had $104 and I backed up 1 year, 104 would reduce to 100. Right, so 108 is going to reduce to a little bit more than 104, but then that 104 is well, sorry, a little bit less, and the 104 will shrink to less than 100. And it has to do with interest on interest, right? Because I'm receiving interest on interest, I can start at smaller than 100 and get there. So working backwards, right, if I have $100, that would turn to $108.16 for similar reasons, right? Interest on interest. So there's a couple examples for you to try, and see if it matches one of the multiple choices here. And then there's also some problems we can do on Blackboard to try this out. So let me show you a feature in Excel that's important, right? So we have this question here. What if R is 5% and I have $95? How long will it take to get 105? Well, the answer is not 2. We know that because it would take 1 year to get from 100 to 105. So that means 95 is not going to quite get to 100. And we're going to solve this. I mean, this can be done with algebra using logarithms. It would look like this, right? We know, or we would say that 95 times 1 plus R to the n is equal to 105, and then we need to solve for n. So we would divide both sides by 95, take the log of both sides, and manipulate that way. But there's actually, and that's a completely valid way to do it. You're welcome to do it that way. But this is a wonderful opportunity to teach an important feature of Excel that you'll need to know, because not all problems can be solved with logarithms. In fact, finding the interest rate for most unknown interest rate problems is mathematically proven to be impossible to do without computational methods. So we're stuck using the computer for a lot of things no matter what. So cute little algebra tricks help a little bit, but really we need a general solution method for things like this. And that is going to be Excel Solver. So let me just show you quick how this works. So if you don't have Solver in your Excel, this is how you get it. So I clicked on File there. So File, Options, Add-ins, Go. So that was File, Options, Add-ins, Go. Now you'll see it, let's see, we'll see it here, but this is not how you get to it. You can't do it this way. You have to go to Go and then see mine is checked. So if yours is not checked, you'll want to check it and hit OK. Okay, so we need Solver. And this is how this works. So I'm going to say present value is 95. And then future value, we're going to leave blank. Interest rate is 5%. And then n is 2, right? That's our guess. Now we know that that's wrong, right? That's not correct. But given our incorrect guess, we can find what the future value would be, right? So we would say 95 times 1 plus R to the n. Now, in this case, in this formula, right, I have created cell references here. C137 is this one, C139 is this one, C140 is is cell C140. But actually, we want to make sure that these don't move. And so I'm going to push F4 here. If you're on a Windows, it's Command T on a Mac. And it puts dollar signs there. What's that doing? That's locking in those references. So no matter where I move this cell, it will still point to the same place. Right? Do you see this? Still points there. This still points there. They would point here and here respectively if I did not put those dollar signs in. Okay. So we're too small, right? We're too small, so we need a little bit more time to get to 105. So let's try 2.01. Not quite. 2.03. 2.08. Oops. That's too far. 2.06. We're getting closer. So we can do guess and check by hand, but in fact, Solver will do that guess and check for you and quit when it gets close enough to the answer that you are looking for. So it's important to recognize that Solver does guess and check, and that means you have to give it a guess, and that can be uncomfortable, right? In this case, the question was, how many years does it take to get to 105? And I put 2 in, and nowhere in the problem does it say 2, right? That was just my guess. Your guess generally doesn't have to be even very good. It just has to be, it has to make sense, like don't do 1,000,000 or don't do -20. Sometimes it'll work anyway, but sometimes giving it a crazy guess will break it. So here's the solver dialog. You can kind of see it here. And the objective is the thing we're trying to do. So our objective is to make this number 105, right? That's what we're trying to accomplish. So our objective is to make that number 105. So how are we going to achieve the objective? Well, we're going to achieve the objective by changing the time it takes to get there, right? Changing n. So see, by changing there, so I'm going to click this and say by changing n. Now there's an area here to add some constraints, so I'm just going to add one. It's not necessary. I mean, this should work just fine as it is, but I'm going to add a constraint. Right, so I will add a constraint that this needs to be bigger than 0. Right? You can't have negative years. It doesn't make sense. Checking this box makes that happen anyway, but just this would be an example of a constraint that you might add to a problem. And but you have lots of flexibility in constraints you can put here. It's just limiting the space, the guess space, to certain to within certain ranges or parameters. So let's fire it up and see what we get. It says solvers found a solution, and there we go, 2.0513. And so Solver is a great general purpose tool for finding answers to questions in this class. In particular, if we have an unknown interest rate or an unknown time to completion, Solver is a really good way to get that done. We can do the same problem on the financial calculator, right? So we would say 95 here, future value is 105, the interest rate is 5%. Payment is going to be 0 because we don't. Payment is periodic payments we get every period, and we don't have any of those. So we can just leave that blank and calculate that, and we get our number once again. So this software does the same kind of iterative calculation. If you're numerically, mathematically inclined, it does something called the secant method, but it just reduces to guess and check and gets us that number for the number of years to get to 105. Okay, so when we come back, we will continue with thinking about applying this to different situations.